Okay, so in this session, we'll take a look at the Poisson and hopefully also the exponential random variables. Okay. And let's start with a binomial problem. So you're going to toss a coin n times. The coin is not necessarily fair, so you're going to assign a probability small p to the probability getting an h. We're going to toss it n times, and let the random variable x be the total number of h's after n tosses of the coin. Okay, we already know how to do this, right? What's the answer? Binomial, right? So the correct answer to this problem, what is x? X is the binomial random variable with parameters small p. So why are we doing this? Okay. So the probability is given by the binomial distribution. That's so the probability that you got small n h's out of capital N tosses of a coin with a probability of getting an h is p is big N choose small n, p to the n, 1 minus p to the big N minus small n. Okay, so as I said, you already know this. All right. Well, what if big N was getting really large? How would you do this? 'Cause you're talking about factorials, and factorials grow very quickly, right? So as a practical matter, it may not be so easy to work out that capital N factorial. Okay. Now we think, okay, so what if p is very small? What if p is very small? Right? If p is very small, then 1 minus p to the n minus n. Anyone remember this? Calculus 2, Taylor series? No? Okay. No problem. No problem. That's okay. Well, let's suppose we want to take the logarithm. So we can take the logarithm of something, manipulate it, and then take the exponential to recover the original thing, right? So we take the logarithm of 1 minus p to big N minus small n. That's the same as big N minus small n logarithm of 1 minus p. Okay? And then for small x, we have the result that logarithm of 1 minus x is equal to this infinite series. Okay? And if you haven't seen Taylor series, that's all right. You will just take that on faith for now. For very small x. Okay? That's how you could get logarithm of 1 minus x as an infinite series. Okay. Now, if x is very small, then x squared is really, really small, and x cubed is even smaller and smaller. So we might, as an approximation, say that when x is really small, then logarithm of 1 minus x is approximately equal to minus x. Okay? So then when we multiply, and what were we looking at? We were looking at logarithm of 1 minus p. Okay? And then we multiply that by n minus n. And we get that for very, very small p, the logarithm of 1 minus p to the n minus n is minus np minus big NP plus small np. Okay. Okay, now I'm not going to make you responsible for the derivation. I just want to show you or to convince you that I'm not just making up the random variable. There's a basis to it. And you see the foundation to it. You'll also see the interpretation of the random variable. Okay? So, as I said, now we were looking at logarithm of 1 minus p to the big N minus small n, so we recover that by exponentiating. So we get that 1 minus p to the small n minus big N is approximately equal to exponential of minus big NP. Yeah.
So where does the small np go?
The small np? Okay. Yeah. So, right. So we could exponentiate that, or we could e to np, but we're going to suppose that, okay, so when you're doing the Poisson random variable, you are, and typically we're looking at things like, let's say, emails in an hour or in a 5-minute interval or something like that. So we are supposing that you can take a small enough, the event that you call a success, if you're thinking of this as a binomial random variable, the event that you call a success occurs so there's a small enough time interval over which the probability of a success is seeing a success is very small. Or there's a small enough area in which detecting something, and that would be called a success. There's a small enough area in which that p is very, very small. So we take p to be very, very small, and then we can drop the np term. Okay, certainly in comparison to the big np term, the small np term can be neglected. Okay, so now we've got that e to the minus p, 1 minus p to the big N minus small n is approximately equal to exponential of minus np. Okay, so something else you might not have seen before. We're trying to approximate the factorials, right? So on your calculator, you probably get 72 factorial, 75 factorial, and past that, your calculator is going to overflow. So then how do you deal with factorials of very large numbers? Okay, well, use Stirling's approximation. You approximate the logarithm of the n factorial, and then you take the exponential of that. Right? So typically, you're not multiplying huge integers. When you ask for the exponential of a very large integer, you are probably getting some sort of an approximation. Or you're using, we'll see the gamma function later, all right, given as an integral. Okay, so once again, we make an approximation for the small n the logarithm of small n factorial, and this is Stirling's approximation. Okay.
So what's an O? With a 0?
Oh, it means there are terms that look like logarithm of n, or things which would be smaller, but not bigger than that.
So the O is a bound?
Yeah, that's a bound. Okay. For the rest of the terms. All right. Okay. So if we apply Stirling's approximation to this term, right, that's your binomial coefficient, right? Because we said the real distribution is the binomial distribution, right? The real random variable is the binomial random variable. And I'm saying that, okay, I'm having trouble dealing with the factorials. So I'm going to get something that approximates the Poisson distribution is going to be approximating a binomial. Okay? The Poisson random variable is approximating a binomial random variable. Okay, so we take the logarithms, and we use Stirling's approximation because we're taking logarithms of factorials, and we get an expression like this. Okay. Okay, and I'm going to make the substitution. Big N minus small n is big N times 1 minus big N over small n. So I'm just rewriting it in those terms, still using the same approximation for the logarithm of the binomial coefficient. And then when we exponentiate that, we will recover an approximation to the binomial coefficient. Okay. Okay, and we do some simplifications. Okay. As I said, we are looking at events that on a small enough interval or in a small enough area, a success has a very small probability. Okay? These are for rare events, at least on a small enough scale. These events are rare. Okay? So, so this small n is the number of actual successes, big N is the number of trials. So if the successes are very small, once again, remember we said logarithm of 1 minus x for x really, really small is equal to minus x, right? That was the from the Taylor series. Okay, so if we apply that then to the expression that we had, then we can say that the logarithm of the binomial coefficient starts to look like this. Okay. And we can simplify that like this. Okay. And remember, n, small n over big N is very small. Probability of a success is very small. So we drop another term which we claim is small. And finally we get that the logarithm of the binomial coefficient is the logarithm of big N to the small n. Okay. And then to recover the binomial coefficient, we exponentiate. So the binomial coefficient is approximately equal to small n to the big N, where when the probability of a success is extremely small.
We don't need to know the proof, right?
No, we don't need to know the proof. But understanding how you got here will help you to interpret the terms in the binomial PMF. Sorry, in the Poisson PMF. Yeah.
Then essentially our binomial p of x is equal to n. Is just going to be n power n into p n into 1 minus p power n minus n?
Yeah, we're going to write it a little differently than that, right? We're going to come up with the nomenclature will be a little different, but okay. So I can replace my in the binomial random variable, or the PMF of the binomial random variable, I can replace this binomial coefficient n choose n by small n, big N to the small n. Okay. So all the approximations that we talked about, we are going to we're going to put them into our into the PMF. right? And I claim that you're going to get an approximation that the probability of small n successes in big N trials, when p is very small, is 1 over small n factorial np to the n e to the minus np. That's your approximation. Okay, now look here. What's that? Minus np. Okay, so first of all, that's a constant, right? This is taking values of small n successes. Okay? Big N was the total number of trials. And P was the probability of a success in each trial. What's this? NP. What's that? What did we see? Say it loud. No? It's the expectation for the binomial. So there's the expectation. Right? I expect one success in 10,000 trials. Right? And I do 50 million trials, so it's 50 million trials times. Yeah. Right. All right. So, and notice that this is happening again. Here's your expectation. Okay, so this is 1 over n, 1 over the number, that number of successes, factorial, times the expectation from the binomial. Remember we said the real random variable is the binomial random variable. This is an approximation to that. Okay, so this is the expectation to the n, e to the minus the expectation, 1 over n factorial, right? So we can understand what the terms are. Okay. So the expectation I'm going to call lambda. So lambda equals np. And I'm going to interpret the expectation as the number of events expected in a given time interval or in an area or something like that. So I have some rare beetle, right? The expected number of beetles in this forest within an acre, right? I have, like 5 emails in a day, so the expected number of emails in a day, or I could break that down in an hour or whatever, right? Okay, so finally, the PMF for the Poisson random variable. Okay? The probability of the number of successes being small n is the expected number of successes to the n over n factorial e to the minus the expected number of successes. Okay? All right, so let's do an example to fix our ideas. Okay, so we spend 1 hour at Lalekchok and we collect some data. So typically your lambda is given by some observations. Okay? So we collect some data and we say that during that time of the day, 1 car enters the traffic circle every 5 seconds. So that is your lambda. Okay? So your lambda is 1 out of 1 success expected every 5 seconds. Okay, so What's the probability that no car enters in some given 5-second interval? So we say, all right, that's a probability that x takes the value 0. Okay. Okay. So remind you of the general formula. The probability that x equals n is lambda to the n over n factorial e to the negative lambda. So the probability that x is equal to 0 is lambda was 1 every 5 seconds. 1 to the 0 over 0 factorial e to the minus, well, 1 every 5 seconds. So that's 1 over e.
So
Yeah.
how do we decide the units for lambda? Like it's 1 every 5 seconds, but 12 per hour.
Okay, right. So what should the units be? You're right, and that will change your lambda. So if you were given the question, how many every 10 minutes, then you'd say, well, lambda is 1 per 5 minutes, so lambda equals 2 per 10 minutes. So you can change your lambda, or you can say, well, how many every 10 minutes? Right. So the question would you can adjust your lambda, or you can adjust something else, depending upon the units you're given in your question. Okay. All right, so next question. What's the probability that exactly one car enters in a 10-second interval? Okay. Well, the expected number of cars in a 5-second interval is 2. So the expected number of cars it was 1. So the expected number of cars in a 10-second interval is 2, right? 1 every 5 seconds is the same as 2 every 10 seconds. So now we can set lambda equal to 2. We have to make our units consistent, okay? So once again, the probability that x equals n is equal to the expected number to the n over n factorial e to the minus expectation. So the probability that x is equal to, the probability that x is equal to 1 in 10 seconds is 2 expected in 10 seconds to the 1 over 1 factorial e to the minus 2 expected in 10 seconds. So that works out to 2 e to the minus 2. Okay? Second example. Yes?
Can we potentially solve the last question of 1 in 10 seconds by doing it with x in 1 second, and 5 seconds there's 1 car, and the other 5 seconds there's no car, and then we add in the first 5 seconds there's no car.
Okay, right. Okay, what we should do is if we're going to stick to lambda is 1 in 5 seconds, then you should say something like, what's the probability of 1 in 10 seconds? That's the probability of a half in 5 seconds. And then things get a bit dicey. Right.
Or would it be different if the way that's described?
The way you described is the right intuitive idea, but no, there's a technicality. We'll get to that in a bit. Okay. Let's say we have 1 biking accident in 2 weeks. Okay? What's the probability of more than 2 accidents in a week? Okay? So, an average or an expectation of 1 every 2 weeks is how much every week? It's a half in a week. Okay? We expect half an accident per week. Okay? And so the probability that x equals, remember, once again, the probability of n successes, in this case n accidents, is the expected number of accidents in a week to the n over n factorial e to the minus the expected number of accidents. Okay, now we were asked for the probability of more than 2 accidents in a week. So, potentially how many accidents are there in a week? Is there a bound to the number of accidents we could have in a week? No. No. Okay, so the probability of more than 2 accidents in a week, what we should probably do is say, what's the probability of 0? What's the probability of 1? What's the probability of 2? Add those together. So that would be the probability of less than or equal to 2 accidents in a week. And then 1 minus that would be the probability of more. Okay. Okay, so again, because we were given 1 per 2 weeks, and we want to work in weeks, then we took our lambda to be a half. Okay? All right, so the probability of more than 2 is 1 minus the probability of 0 minus the probability of 1 accident minus the probability of 2 accidents. Then, well, and this is the probability, the formula that we would use for each one of those terms, right? And I'll let you work those out. Okay. And, okay, so there's an exercise for you to try on your own. Giving you the answers that you're supposed to get. Okay, let's talk about the Poisson random variable then. Okay, so this is how we think about it. There's a time interval, and then there's a certain number of occurrences of something that I could consider a success. Right? I'm looking at the occurrences of some rare beetle every square meter. I'm looking at the number of emails in an hour or in a second, depending upon what the traffic is like. Okay. So, or power failures in a week, let's say. Okay. Originally, the problem was, how do I allocate for widows' pensions? Right? Widows of cavalry officers whose horses have kicked them to death get a pension. I can't possibly know how many mischievous horses there are this year. Okay, but I have to deal with it. I have to budget, right? So, okay. So, what we're supposing here is that if we're looking at disjoint intervals, or we're breaking up an area into disjoint pieces, then the number of outcomes is going to be independent in each piece or each interval. So just because I got three emails in this hour, it doesn't tell me anything about how many emails in the next hour. Okay. Okay? And if I take a short enough interval, or if I take a small enough region to look for a success in, then the number of the probability that a single event will occur. So we're looking at really, really small intervals. So within an extremely small interval, say a microsecond, maybe, I'm going to get one email or I'm going to get 0 most of the time. So I can make this assumption that I'm going to get 1 or 0 successes. Or in a small enough area, I'm going to get 1 beetle or 0 beetles. Right? And the number of outcomes outside of a region, so then you have a proportionality, and we're sort of inherently doing it when we were changing our lambda. We were assuming a proportionality, right? And what's happening in this region doesn't depend upon what's happening in that region. So these are all assumptions when we're talking about applying the Poisson random variable.
What's the difference between this one and the previous one? In the previous one as well, we're saying that it's the number of outcomes in a single period is different from the number of outcomes.
Yeah, so you're right. Okay, so that's a little bit repetitive. The main thing here is that you have this proportionality. If I have expectation of 1 per meter, then I'm going to have an expectation of 2 per 2 meters, or something like that. That's what we're saying. Okay? Yeah.
If you get 3 emails in 1 hour on some random day,
Yeah.
and if you want to find out how many emails you will get in 2 hours on some other random day, won't it be 6?
No. Okay. So you might be saying at the same time of day on a weekday. You have to be careful about variational seasonal variations of things, right? People might be eating more. Okay. People are maybe eating more ice cream in an hour in the summer than they are in the winter or something like that, right? Okay, so when we're assuming this, we're supposing that our lambdas are not changing, and so you have to make sure whether that's a valid thing or not, right? So I would say that if it's something like McDonald's, they know which days are comparable to different days. They might be saying the lunch hour, the lambda is this, but the breakfast timing, the lambda is that, or something like that. Okay. Okay, and you can find small enough regions or small enough intervals to look for a success that the probability of very many outcomes, very many successes is negligible. Okay, and then so this is what you get. As we said before, the probability of x successes with an expectation lambda is e to the negative lambda expectation to the x over x factorial. X can take all non-negative integer values, and x is never anything else. So there's your PMF. Okay, and we built this thing saying that lambda was the expectation. And it turns out then that the variance for the Poisson random variable is also lambda. Okay, and remember when we started, we were making approximations. We started with a binomial random variable. So we were making all of this business as an approximation to the binomial random variable. Okay, so these two are linked in this way. Okay, so are there any questions? Okay, so now we go on to another random variable, which is called the exponential random variable, and these two are very tightly linked with each other. Okay. Okay, so the Poisson distribution is concerned with events that occur in a given interval or region. So I can imagine a timeline, and I break it up into, I don't know, maybe 5-minute intervals or whatever. And now you're concerned with, well, 3 occurred in this time, and 2 in this time, and 5 in that time, and so on. Okay? So that's what the Poisson random variable is concerned with, is how many successes occur. Okay? Now, the exponential random variable is concerned with the times between Poisson distributed events. If you know that the events are Poisson distributed, or that that's a reasonable approximation, then what's the time between these events? Okay, so I've got time running, and one of these Poisson distributed events happens at this time. Okay, an email arrives. I'm saying the number of emails arriving is a Poisson distributed. Okay, so an email arrives. And then I ask, what's the probability that the next email arrives within 3 hours, or let's say, something like that. Okay, so the time, the exponential distribution is all about the time between Poisson distributed events. Okay, the successes themselves are Poisson distributed. The time between event, the nth event and the n plus 1 event, that time interval is exponentially distributed. Okay, so as an example, you have power failures occur once every 2 hours, let's say. So we would say that's the average, 1 per 2 hours. Okay, then we would say something like, over the next hour, what's the probability of 0 power failures over the next 2 hours, let's say, or whatever, right? So that would be the number of power failures would be the Poisson distribution, or you would be using the Poisson distribution. What's the probability that a power failure occurs between 10 and 25 minutes from now? That probability, that's the exponential distribution is telling you that. Okay, so once again, let me remind you of the PMF for the Poisson distribution, and that's a discrete random variable. The exponential random variable, on the other hand, is a continuous random variable. Okay, so this is that. So if x is my Poisson random variable, I have events which are Poisson distributed with an expectation of lambda events. I expect lambda events to occur in this time interval. Okay? Then the related exponential distribution, let's call that random variable then y for the exponential random variable. That's given by the lambda. That was the expectation from the Poisson distribution. Lambda e to the negative lambda y for y greater than 0 and 0 otherwise. Okay? All right, so these two, this is the Poisson. Let's call that one x. And then the related exponential distribution, that there's this PDF for the exponential random variable, and we're going to call that one y. Okay? Notice that it's 0 to the left of 0, and it's exponentially decaying to the right of 0. Okay?
We have to differentiate it for probability.
No, okay, right. So this is the PDF. So if you want a probability, you have to integrate. Okay. Okay, we also use this notation. Okay. Lambda is the number of successes expected in a unit time, in some time interval. We take beta is equal to 1 over lambda, and then we would write the PDF for the exponential random variable this way. Okay? What do you think beta is? Okay? If I've got 5 mosquito bites per hour is my lambda, then what is beta? 1 over lambda, what's beta? All right, it's the expected interval between mosquito bites. Okay? All right? And so here, so beta is the expected, is the length between the average, the expected time between mosquito bites. Y is the time. Right? So, right, and you get 1 over beta. So what do you think what's the expectation for y? If lambda was the expectation for x, what's the expectation for y? This beta. Right? Right? 5 mosquito bites per hour. I take the reciprocal of that. That's the expected time between mosquito bites. Okay? So the expectation is beta. And the variance is beta squared. Okay, so let's do a few examples with that one. We are, let's say, averaging 1 power failure. We're averaging 2 power failures per hour. Okay? Okay, I expect 2 power failures in an hour. What is the expected time between power failures? Half an hour, right? Okay, what is the probability of less than 1 hour interval between power failures? Oh, okay, so we have to go back to our PDF for the exponential distribution, because now we're talking about the time interval. Okay, so once again, we were given 2 power failures per hour. So beta equals 1 over lambda. 1 over 2 is the average time, half an hour in this case. The average time between power failures. Okay? So, to get the probability of an interval of a length of 1 hour between power failures, we have to integrate the PDF for the exponential random variable. Okay? So, remember? So, the probability that y takes values between 0 and 1, well, you integrate the PDF for y between 0 and 1. So, y equals 0 to y equals 1. 1 over beta e to the negative y over beta dy. Okay? And that works out to 1 minus e to the minus 2. Okay. How would you work out the probability of there being more than 1 hour between failures? Okay. You could take 1 minus the probability of this thing that we just found. And that would be e to the minus 2. Okay? All right. Any questions so far? Okay. Next example. So, well, okay, so another kind of failure. We're supposing that something lasts for beta equals 5 years, on average, something lasts for beta equals 5 years before failure. What's the probability that the component will last longer than 8 years? Well, that'll be 1 minus e to the minus 8 over 5. Okay? All right, so the probability that y is bigger than 8, well, we can either integrate the PDF from 8 to infinity, an improper integral, or we can take 1 minus the probability that y goes from minus infinity to, that y lies between minus infinity to 8. Okay? Yes? Right, that's why the PDF is 0 to the left of 0. Right? Well, but in principle, for any, this is true for any PDF. Right? Yeah. Right. So let's do the integration to infinity this time. Right? Yeah. Yeah. Okay. No. The probability. Okay. All right. What does the PDF look like? The PDF is 0 over here, and then it's dropping off exponentially like this. So we could integrate from 0, let's say, to 8, find the area under the curve by the integration, and then we could take 1 minus that to find the area from 8 to infinity, or we can do the integral from 8 to infinity, remembering that we are talking about an improper integral. So you should actually, if you're being very strict, you should be doing integral from 8 to b and then taking the limit as b goes to infinity. Okay? But anyways, if I take, okay, so 1 over beta, integral from 8 to infinity, e to the minus t over beta, dt, okay, well that will work out to e to the minus 8 over 5. Out 0.2. Okay, so again, if you're selling, let's say you're selling a mobile phone, you give guarantees that it'll, if you were to give a guarantee that it will last a certain amount of time, you probably you should have some idea of how long you expect it to last and so on, right? And then you can work out how many times you'll have to you might have to give a refund or give some repairs or something like that, right? Okay. Now, what's the CDF again? If I have a PDF, what's the CDF? Okay. So, the CDF evaluated at some value is the probability that the random variable takes values between minus infinity and that value, right? Okay, well, okay. So the CDF evaluated at B is the PDF integrated from minus infinity to B, right? Okay. So this was the PDF for y, for the exponential random variable, right? And if I want the CDF evaluated at B, let's say, then I integrate from minus infinity to B this PDF. Okay, and I don't bother integrating from minus infinity to 0 because that's unnecessary. Okay, so the CDF for y, remember, for PDFs I'm using small f, and for CDFs I'm using capital F. So the CDF for y evaluated at t, that's the probability that y will take values from minus infinity to t. So I integrate from minus infinity to t the PDF for y dy. Well, again, you have this behavior from minus infinity to 0. It's 0 anyways. So I may as well just integrate from y equals 0 to y equals t. And then on that interval, the PDF has the form lambda e to the negative lambda y. And that will give me 1 minus exponential of negative lambda t. Okay, for t greater than 0, of course. Okay. And remember, lambda, we're using lambda and beta here, so this would be minus t over beta if you wanted. Do you want to see how to get this?
Sorry,
okay. All right. Okay. All right. So the probability that y takes a value bigger than or equal to t is 1 minus the probability we just calculated. So that's e to the negative lambda t, or same thing, e to the minus t over beta. So now we have the CDF. Okay? And 1 minus the c. 1. Right? Okay. Okay, so now we come to a very interesting property. Suppose we say that power failures happen on an average of 1 every 10 hours. We just had a power failure. What's the probability that the next power failure will be in more than 15 hours? Why is that e to the minus 1.5? Because we just did that problem, right? E to the minus t over beta. So e to the minus 15 and beta was 10. E to the minus 1.5. Okay? right. Oh, well, we just somebody's been taking measurements over the last 12 years and they've come to, you just said 10 hours. Well, yeah, so lambda is 1 every 10 hours, so 1 over 10 for beta, right? Oh, right. Okay? So, sorry, so beta is equals to 10, right? And t we were being asked was 15. So e to the minus 15 over 10, e to the minus 1.5.
Lambda is 10, right?
No. Well, we have 1 power failure every 10 hours. So the expected amount of time between power failures is what? 10. Okay. Yeah. Right. We expect 1/10 of a power failure per hour.
So 1 over 10 is that.
Yeah. Yeah. Okay. All right. Times between buses. Number of buses, the number of a certain route. The number of buses if I'm waiting at a bus stop is this many buses per hour or something, right? So let's say the bus on my route should come by every 10 minutes. Okay? I've waited 8 minutes. What's the probability that the bus will come in the next 4 minutes? Okay? So that's a conditional probability. So let's be a little bit careful with that. Okay. Yeah. Yeah. Okay? So we're given one bus every 10 minutes. So I want to work in minutes, so let's work that. We'll say that that's the same as 0.1 bus arrivals per minute. I'm asked for the conditional probability. What's the probability? Okay, so I started timing. I got to 8 minutes. And then I'm looking at what's the probability that the time that I'm waiting is another 4 minutes, is less than or equal to another 4 minutes. So it could arrive right now, or the probability that it could arrive right now up to 4 more minutes, and I've already been counting 8 minutes. Okay? So what's the probability that the waiting time is less than 12, given that the waiting time is already bigger than 8? Okay? Is that all right? This is a conditional probability that I've been asked for. Okay. Well, okay. The probability, what's conditional probability? Probability of A given B is the probability of A intersection B divided by the probability of B, right? So this is the probability that y is less than or equal to 12 and that y is bigger than 8 divided by the probability that y is greater than 8. Okay? Okay. Well, if y is less than or equal to 12 and y is bigger than 8, that means I'm being asked for the probability that y, this numerator probability here, is the same as the probability of y lying between 8 and 12. Okay? Divided by the probability that y is bigger than 8. Oh, what does this mean? The probability y, the probability that y is less than, see, this is the CDF then, right? So here's 8, here's 12. If I want this probability in the blue here, that area under the curve, I can take the CDF at 12, I can subtract the CDF at 8, and it gives me the probability that y lies between 8 and 12. Okay, so that's the CDF at 12 minus the CDF at 8, and the probability that y is less than 8 would be the CDF at 8. So the probability that y is bigger than 8 is 1 minus the CDF at 8. Okay, so I've rewritten everything in terms of the CDF, which we've already found. Okay, so now we can put those in. Okay, so that's 1 minus the exponential. That's minus 12 over 10. Minus 1 minus the exponential. That's 8 over 10. That's your t over beta. T with 8 and t with... Yeah. Divided by the exponential of minus 0.1 over 8. Okay, so this is finally what when I simplify all of this, I get this. But this is just the CDF at 4. So that's the probability that y is less than or equal to 4. So I expect a bus every 10 minutes. I've been waiting 8 minutes. What's the probability that I have to wait between 0 and 4 minutes? More. Well, that's just the probability of waiting between 0 and 4. It's not affected by the fact that I've already waited so long at all. There's no reason to believe that because something hasn't, well, in this particular case, if things are exponentially distributed, the fact that you've already waited so long has no bearing on how much longer you have to wait. Yes?
Slide.
Yeah.
What's that symbol on the left? P of y less than equal to 8 plus 4, and then there's a symbol. What does that mean?
The probability that you have to wait. Okay, so we thought we started our clock. We counted that we had waited 8 minutes. So what's the probability that we have to wait another 4 minutes, or less than or equal to another 4 minutes? Means that, well, we'd be waiting less than or equal to 12 minutes from the time that we started counting.
That like vertical line is an and?
No, that's a conditional probability. Okay. All right. Okay, so once again, this is very important. The probability that you have to wait another 4 minutes has nothing to do with the probability that you've already waited 8. Yes?
So I can get that. Why would it not affect it? Because given that I'll have been there for 8 minutes.
Yeah?
That should affect my calculation of the probability that.
Yeah, only it didn't, right? Yeah, I know. Intuitively, you're right. It should matter, but buses don't care. Buses don't care. Okay. All right. So this is what we call the memoryless property. The exponential random variable has this very peculiar property, or at least non-intuitive property, that it is memoryless. What's happened before has nothing to do with how much longer you have to wait. Okay. All right. So instead of 8 plus 4, if we run through the same business with x plus y, you get the same result. Okay, so this is the probability that even though I've weighted x, the probability of weighting another y, given that I've already weighted x, is just the probability of waiting for y. Okay, so memoryless property of the exponential, a random variable. This is the only random variable which has this property. Yeah? This is important, right? This is like the thing that, if there's like 4 things that you should remember from this course for the rest of your life, this is one of those things, right? Okay, I'll see you next week.